In the previous lecture, we talked about evidence. I was asking why and how should you trust the stories that modern science tells about the origins of everything, about the universe, the stars, the planet, and so on. And I focused on the idea of evidence, arguing that science focuses above all on evidence. So in the light of that discussion, here's a question you might want to ask at a flagging cocktail party. It is, how did the universe begin? Now, I think there's a sporting chance that you'll actually get an answer to that question. So you might have to go to the next step. And the next step is the next question, which is, so how do you know? Were you there? What's your evidence? How can we know about something as remote as the origins of everything? What I want to do in this lecture is to approach that question. I'll be describing the modern answer in the next lecture. But what I want to do is show how over several centuries, evidence and arguments slowly built up that provided the foundations for the modern scientific answer to the most fundamental historical question of all, which is, how did everything begin? And we'll see that the crucial breakthroughs came in the 1920s. Now, one reason for going back into the past and looking at how the modern story was constructed is so that we avoid taking the modern answer for granted. It's all too easy. You'll hear about Big Bang cosmology and you'll think, oh, that's the way it is. If we see how painstakingly over many centuries that modern answer was constructed, it may be a reminder of the power of evidence and the difficulty and effort with which the modern scientific claims about the past were constructed. So that's what I want to do. I want to look at how over several centuries evidence accumulated from which the modern answer was constructed to this deepest of all possible questions. So we're focusing on evidence. Now, this is something I'll do in many of these lectures. Instead of just describing the modern answer, I want to contrast it with traditional answers, both to see some of the similarities and to see some of the differences between modern scientific accounts of reality and the traditional accounts that have shaped people's thinking for so long in human history. As far as we know, all societies have asked this question: how did everything begin? And as far as we know also, many societies have offered deep, rich, and powerful answers to that question. We'll look at some of them in the next lecture before describing the modern answer to this question. But here, I want to focus just on one tradition, and that's the Western Christian tradition. And the reason for that is not that rich and powerful ideas about the origins of everything didn't emerge anywhere else. It's simply that the modern answer emerged out of the Western cultural tradition, out of that particular cultural environment. So, let's look at traditional ideas within Christian culture about cosmology and the origins of the universe. Christian ideas about the universe were dominated for almost 1800 years, and still to some extent today for many people, by a combination of Christian theology, which of course saw God, the Christian God, as the ultimate creator of everything, the prime mover of this process, the ultimate explanation for everything. That's the first part. And secondly, a model of the universe that was created by an astronomer and mathematician, Ptolemy of Alexandria, whose dates were 90 to 168 CE. So he lived in the 2nd century after Christ. And Ptolemy's model, I'll argue, counts as scientific by the best standards of his time. What Ptolemy's model did was to put the Earth at the center of the universe. So this is an Earth-centered model of the universe. Now, I want to look briefly at Ptolemy's model. In the Western tradition, it was hugely powerful. It was influential, as I said, for 1,500 years before it started losing some of its power. By the standards of the time, Ptolemy's model was good, empirical, evidence-based science. However, It was not the only scientific account available in the Mediterranean world 2,000 years ago. Some astronomers, such as the Greek Aristarchus, who flourished 4 centuries before Ptolemy, had argued again on the basis of the best evidence available and some quite sophisticated mathematics and observation that in fact the sun was at the center of the universe. So the idea of an Earth-centered universe was not the only model of the cosmos available. There was also this other quite powerful evidence-based model of a sun-based universe. Why did Ptolemy's version end up dominating? Well, it's a combination of 2 things. And perhaps the most powerful reason is because it acquired eventually the backing of the Christian church. It dominated thought in the Christian world as a result for at least 1,500 years. But as I said, it was also a pretty good scientific account in the sense that it was based on a lot of careful thought, careful observation, and evidence. So, what did Ptolemy's model of the universe look like? Let me describe it briefly. Ptolemy's model presupposed a universe with a radius, and we're sort of calculating backwards to estimate this. He didn't put it quite like this, of course, but with a radius of about 80 million miles, a diameter, in other words, of 160 million miles. Now, as it turns out, this is quite close to the true distance from the Earth to the Sun. At the center of this universe was the Earth itself. Around it were several perfect, transparent, rotating spheres. These were solid and crystalline. And what they did was they carried the heavenly bodies. So they carried the sun, the stars, the planets, some of the comets. Each of them moved in different ways, and it was the movements of those spheres that explain the way that heavenly bodies seem to move in the sky. But there was another crucial point to his model of the universe, and it was this. The spheres existed in a heavenly realm that was perfect. This was a realm of perfection. This was the divine realm, Augustine's city of God, the realm of God. The earthly sublunar zone, the world beneath the moon, was the world of imperfection. So here you have a universe split into 2 realms, a heavenly perfect realm and an imperfect earthly zone. Now, both evidence and authority gave powerful support to this model. First, the evidence. It did a very good job of explaining the movements of heavenly bodies. And in fact, that was a result of the fact that it was based on very, very careful observation and a lot of very careful and hard calculation. It was designed very well. It also explains something else that we're all familiar with, and that's a common sense fact about reality. It's that the Earth appears to be still. So it made sense to a lot of people to say that the Earth is the still center of this entire thing. Think about it. If the Earth is moving at many thousands of miles an hour, shouldn't we feel the wind rushing past us? If we throw a ball into the air, shouldn't it fall down to the right or the left or in front of us or behind us? Intuitively, the idea seems right. Ptolemy's model was also supported by authority. It was supported by the authority of the Catholic Church, which had argued since the 3rd century CE that God created the universe in about 4000 BCE, about 4,000 years before Ptolemy wrote. And the Church eventually put its backing behind Ptolemy's model of the universe. So these 2 things, evidence and authority, explain the power and authority of this model of the universe. Then, from the 16th century, new evidence and questions began to accumulate that undermined this familiar traditional story. Now we're going to move 1,500 years forward to the 16th century, to the early days of the scientific revolution. And one of the main features of the scientific revolution in Europe was, of course, that authority began to give way more and more to evidence. Authority, the fact that something had been said for 1,000 years, became less and less a reason for accepting it. And more, people such as Francis Bacon demanded evidence for any large claim he made about the universe. And this is when the Ptolemaic model began to break down. Here are some of the reasons. The first type of problem emerged was really logical and mathematical. The Polish-born astronomer Nicolaus Copernicus, whose dates are 1473 to 1543, showed that if we switch our thinking in a sort of gestalt switch of the sort I've mentioned before, like the sort of switch that Ant in the helicopter underwent, and if we suppose that perhaps, let's consider the possibility that the Earth is moving, that the Earth, like all the planets, is actually orbiting the Sun. Let's consider the possibility of a sun-centered universe. If we do this, he showed, then some of the problems of the Ptolemaic system, and it had quite a few, seem to vanish. Let me give one illustration. This is the so-called retrograde motion of the planets. Every year, if you watch the orbits of the planets, or you watch the movements of the planets in the sky, they seem to move and then suddenly stop and reverse and move back in a sort of curve and then carry on in the same direction. The Ptolemaic system always struggled to deal with that. You had to add various sort of mechanisms to this machinery in order to explain it. They were known as epicycles, but it was a bit ad hoc and a bit arbitrary. What Copernicus showed is that if you assume that the Earth is orbiting around the Sun along with the planets, you're bound to see something like this. So Copernicus proved that a sun-centered model probably made as much sense as the traditional one. A second type of evidence was based on careful observation of planetary movements and combined with careful mathematics. A Danish astronomer, Tycho Brahe, who lived 1546 to 1601 and is widely regarded as probably the finest of all naked eye astronomers, showed a curious thing. He showed that comets appear to be moving not around the Earth, but sort of through the crystalline spheres. And this immediately suggested perhaps the crystalline spheres weren't so rigid or as impenetrable as the Ptolemaic system assumed. And here's another problem. A German astronomer and mathematician, and actually he was an astrologer as well, Johannes Kepler, who lived from 1571 to 1630, showed that the planets don't move in the perfect circles that Ptolemy's system required. After all, this was a realm of perfection. He showed that, in fact, they move in ellipses, in sort of squashed circles. There was a third type of problem, and this derived from new observational techniques, a new observational technology, the telescope. Galileo Galilei, the great Italian astronomer, whose dates are 1564 to 1642, was one of the first astronomers to use telescopes. And what he showed, or one of the things he showed, was that the heavens are far from perfect. He was able to show, for example, that if you look at the sun, it seems to have spots. I mean, they look like a rash on someone's face. They come, they go. This was not quite what the Ptolemaic system required. Now, that may seem rather trivial, but it's actually an idea that had really fundamental implications. And the main implication was this. Ptolemy, we've seen, had divided the universe, in effect, into two realms, a perfect heavenly realm and a very imperfect earthly realm. If Galileo was right, that in fact the heavenly realm too was imperfect, if its circles were ellipses, if Jupiter had red spots on it, what did this mean? Well, one possibility was that the two realms weren't so separate. Perhaps, and it was Newton who would first say this very clearly, perhaps all of the universe operated according to the same fundamental laws. That was a profound breakthrough in thinking about cosmology and the universe. Now, the new Earth-centered system also faced problems of its own, and one of the main ones was, why don't we feel the Earth moving? Why don't we feel the wind rushing past us? Well, here it was simply a matter of some careful logic and thinking, and Galileo was one of the people who explained this anomaly. He explained that we don't experience our movement through space because everything around us shares it. Now, think about this. If you're traveling in a plane and you throw a ball up in the air, what do you expect to happen? Do you expect it to sort of whiz to the back at 500 miles an hour? No. You expect it to just drop placidly back into your hand. And that's because everything in the plane is moving. along with you. So this is why we don't experience movement on the Earth. Right. We have the Ptolemaic system breaking down, a number of new ideas emerging, and during the scientific revolution of the 17th century, a new model of the universe emerges, and it builds on these mathematical, logical, and observational findings. One of the crucial figures in the scientific revolution is, of course, Isaac Newton. His dates are 1642 to 1727. In 1687, he publishes the Principia Mathematica. And what he did here is, for the first time, to construct a law of the universe that clearly applied both to the heavens and on Earth. He showed that Kepler's laws of planetary motion with elliptical orbits made sense if you made one assumption. It's a very simple one. And the assumption is that there exists throughout the universe a single force, which he called gravity, by which every object with mass is attracted to every other object with mass. And he argued, to be more precise, that the power of gravity depended on the mass of the objects involved and the distance between them. It increased as they got more massive. It decreased as the distance between them increased. Now, this became the basis for a whole new view of the universe. The cosmology that emerged out of the scientific revolution had no obvious limits in time or space. And what this suggested was that the universe might be, though no one was sure, infinitely large and infinitely old. But the idea of an infinitely large universe raised new problems. It was no perfect solution to the problems that had been raised about Ptolemy's universe. Kepler had pointed out, for example, if the universe was infinite, there ought to be in the universe an infinite number of stars, and they ought to be emitting an infinite amount of heat and light, and everyone on Earth, and you and me, should be burnt to a crisp. And that's patently what's not happening. That was one problem. In an infinite universe, there ought to be too much energy, too much light, too much heat. A second problem only really emerged in the 19th century, and it's linked to the second law of thermodynamics that I discussed in Lecture 3. The second law of thermodynamics implies that the amount of usable energy in the universe is slowly running down. And a consequence of that, of course, is that in an infinite universe, there ought to be no usable energy. And again, this was patently not true. So there were always problems with an infinite universe, but probably the consensus for several centuries was that this was at least a possible picture of how the universe was. Now let's look at how these various problems were resolved in the 20th century with the appearance of an entirely new model of the universe. And the crucial figure here is an American astronomer, Edwin Hubble, whose dates are 1889 to 1953. The Hubble Space Telescope, of course, is named after him. And he did his crucial work in the late 1920s. He came up with evidence in that period suggesting something that seemed, for most astronomers and cosmologists, completely unexpected. And this was that the universe seemed to be expanding. Everyone had assumed that infinite or finite, it was sort of fixed in size. What he showed was that it seemed to be expanding. And the crucial piece of evidence was known as the red shift. Now, I'll come back to the red shift in a minute, but briefly let me talk about Hubble, because he's himself a fascinating character. He was one of the first American Rhodes Scholars to study at Oxford. And Bill Bryson, in his delightful short history of everything, which I'll quote several times because it's a wonderful short introduction to the history of science, says this of Hubble's experience as a Rhodes Scholar. 3 years of English life evidently turned his head, for he returned to Wheaton, Illinois, his hometown, in 1913, wearing an Inverness cape, smoking a pipe, and talking with a peculiarly orotund accent. Not quite British, but not quite not. And it would remain with him for the rest of his life. It's as if he was trying to be Sherlock Holmes. He clearly had pretensions, but he was also a remarkably lucky person. He was a superb athlete. Here's Bryson again on Hubble as a school athlete. At a single high school track meeting in 1906, writes Bryson, he won the pole vault, shot put, discus, hammer throw, standing high jump and running high jump, and was on the winning mile relay team. You can count them. That's 7 first places in one meeting. He could have made a career as an athlete. He could have made a career as a boxer. In fact, he ended up as an astronomer. One more thing about Hubble. He never won a Nobel Prize, despite having made one of the great discoveries of the 20th century. And this rankled. And the reason he didn't was because astronomy was not recognized as a branch of physics. So he couldn't award Nobel Prizes for astronomy. And Hubble spent most of the last part of his life in a bitter campaign to persuade the awarders of the Nobel Prize that astronomy should be regarded as a branch of physics. Okay, back to Hubble's achievement in the 20s. To understand what he did, we must go back to the 19th century. We must go further back in time. And what we must look at is attempts to map the universe. These became much more sophisticated in the 19th century. And there were 2 crucial problems. Can you measure the position of stars? And that meant essentially, can you measure how far away they are from the Earth? And secondly, can you measure their motion? Can you measure whether they're moving towards us or away from us? Now, if you can do those 2 things, you've got a much better idea of the shape of the universe. So this is what 19th century astronomers spent a lot of time doing. Now let's take these in turn. First, how far away are the stars? The first precise measurements of stars, of distances to stars, were made in the 19th century, and they were based on the principle of parallax, which was very familiar to Greek astronomers. They knew how to do it. They just didn't have the observational equipment needed to do it. What's parallax? Hold your finger up in front of you, then waggle your head back from side to side, okay, like this. Now, what you'll notice is that the finger seems to move against the background. Something similar happens with the Earth and stars. The Earth orbits around the sun, so it's moving back and forth. That's like me waggling my head. A near star, we can imagine, is in the position of the finger, and remote stars count as the background. So that's how parallax works with stars. Now, the Greeks understood that in principle, if I knew several things, for example, I knew how distant the remote stars were, and I can take them as infinite, if you like, that'll do it. I can measure how far the near star seems to move, and I know how far my head is moving or how far the Earth is moving. If I know these 3 things, I can use trigonometry to find out how far my finger is or how far the nearest star is. So that's parallax. The principle is very simple. It requires high school trigonometry. Unfortunately, even the nearest stars are so remote that we cannot see the shifts with the naked eye. And that's why the first precise measurements of stellar parallax and distances to near stars were made in the 19th century. They depended on improved telescopes and more careful observations. And they were not made until about 1838. And what they showed, as we've seen already, is that even the nearest stars are trillions of miles away. Now that tells you something about nearby stars. What about more remote stars? Finding a way of measuring distances to more remote stars was the work of another American astronomer, Henrietta Leavitt, whose dates are 1868 to 1921. Henrietta Leavitt is not generally given enough credit in this story, and it's partly, quite frankly, because she was a woman in a quite patriarchal world. But what she did was something very, very impressive indeed. She developed a way of measuring the distance to more remote stars. She studied Cepheid variables. They're named after the constellation Cepheus, in which they were first found, and they're stars which pulse. Their light increases and fades in a regular pattern. And we now know this is because they're very old stars in the final stages of their life. What she found is that the cycle of the pulse correlates with the size and brightness of the star. In other words, if you know the cycle, you know how bright that star is and how big it is, because size or mass and brightness correlate as well. Now, this gave you a way of measuring their distance. You measure their apparent brightness on Earth. You know now what their real brightness is, and you can estimate how much light has been lost between you and the star. and therefore you can estimate its distance. So Cepheids gave us a sort of benchmark, a candlestick out there to measure the distance to more remote stars. And it was using Cepheids that Hubble made his first great discovery. He found that there were some Cepheids outside our galaxy, the Milky Way. This was revolutionary, for it showed that the universe consisted, as the philosopher Kant had suggested, of many, many galaxies, not just of one. That was already a revolutionary idea for astronomers. Now we need to ask, are the stars moving? How can we tell if remote stars are moving? And to understand this, we need to go back to 1814 to the work of a German glassmaker, Joseph von Fraunhofer. He invented the spectroscope. What the spectroscope does is, it's like a prism. It takes light, it breaks it up into its various frequencies, into its component wavelengths. This means you can study light, including the light from stars, and you can see the different frequencies it contained. What Fraunhofer saw was that if you take starlight, you'll very often find absorption lines. These are dark lines where some of the energy of a particular frequency seems to have vanished. What are these? What's going on here? Laboratory experiments showed that these absorption lines corresponded to particular elements in the stars, because each element absorbs light at a particular frequency. So hydrogen, for example, absorbs at a particular frequency or a particular group of frequencies, and the same for other elements. So using the spectroscope, you can tell the chemical composition and temperatures of stars. That itself was a remarkable achievement. But more was to follow. In the late 19th century, another American astronomer, Vesto Slipher, who's working at the Lowell Observatory in Flagstaff, Arizona, showed that some stellar absorption lines looked odd. They didn't quite correspond to the elements you expected. They seemed to be shifted either towards lower frequencies, towards the red end, they were red shifted in other words, or to higher frequencies, to the blue end, they were blue shifted. What was going on? What does it mean if you suddenly find the hydrogen line is shifted? He interpreted these as red shifts, as the results of a Doppler effect. Now, we all know the Doppler effect. An ambulance is coming towards you, the sound goes, mm. Why does it drop? As it's coming towards you, the sound waves are sort of squashed up, so the pitch seems to be increased. As it's moving away from you, the sound waves seem to be stretched out, so the pitch drops. And what Slipher said is something like this is going on with starlight as well. If a star is moving away from us very fast, or a distant galaxy, the waves are going to be stretched out. They're going to be red shifted. If it's moving towards us, they'll be blue shifted. It's a Doppler effect. And it's using these devices that Hubble transformed cosmology. He combined the technique for measuring the distance to stars and the technique for measuring their movements, and he showed in the 1920s that all the most remote objects in the universe were red shifted, all of them. This was already strange. They're all moving away from us. Then he showed a second thing even more profound. This was that the further away they were, the more red-shifted they are. In other words, what this is showing is that the further away an object is, the faster it's moving away from us. What does this mean? Well, if our part of the universe is typical, what it means is that the entire universe is expanding. It's as if we're sitting on part of a hand grenade and we're watching other bits flying away from us, and the most remote bits are going to be flying away from us faster than the others. A Belgian astronomer, Georges Lemaitre, pointed out this implied that in the distant past, everything in the universe must have been crushed into a single, tiny, dense, hot point. A primeval atom, as he called it. And it followed, remarkably, that by measuring the rate of expansion of the universe, we could date the moment of creation. This was a remarkable breakthrough and a remarkable achievement. It solved the problems posed by an infinite universe, for an expanding universe had to be finite, and it had to contain finite amounts of light and heat. It also fitted well with Einstein's recent theories, which, though he was reluctant to admit this at first, implied that the universe must be either expanding or contracting. Nevertheless, for 2 decades, hardly anyone took the idea seriously. The name Big Bang was coined for it by one of the naysayers, Fred Hoyle, who we're going to meet again. He'd worked with Gamow. He used the phrase with derision. This was just a Big Bang that this is all about. In fact, the theory, as we'll see in the next lecture, would be clinched in the 1960s. So what I've done in this lecture is show how evidence accumulated over many, many centuries for a rather startling new image of the universe. And it showed that the universe was expanding. And that meant that the universe had a beginning. And that meant that the universe had a history. And that is why the universe deserves to be regarded as a part of history. And that's why it's part of this big history course. Thank you.